Hi, and welcome to 9.5 Recoil and Inelastic. We're going to do recoil and explosion type of law of conservation of momentum problems in this activity. It says, number one, a 5 kilogram gun is initially at rest and it's free to move. So when a 0.015 kilogram bullet leaves the gun with a speed of 750 meters per second, what is the speed of the gun? So you have your gun, and you have your bullet inside of the gun, and initially they're both at rest. So the initial velocity is 0 meters per second. So even though the gun has a mass of 5 kilograms and the bullet has a mass, it's a lot smaller, it's 0.015 kilograms. Even though these things have mass, they don't have any velocity, and therefore the initial momentum of the system is also 0. Now, after the explosion, the bullet's going to go flying, and the gun will experience what's called a recoil velocity. It's going to get pushed back into the shooter's hand. So it looks something like this. Sure, the bullet's going super fast, all right? The velocity is 750 meters per second, and we could call that V2F, the final velocity of the second mass. But there's also this, so it's going this direction. The gun gets pushed back in this direction. It also has some velocity in this other direction, V1F. How do we know that it's being pushed back? Why does it get pushed back? That's kind of a weird idea. Well, if we knew that the initial momentum was 0, then the total momentum of the bullet, so the bullet definitely has some momentum, P2F, plus the momentum of the gun, P1F. When you add those two vectors together, you're going to get 0 kilogram meters per second as well, because of the law of conservation of momentum. It states that the initial momentum is supposed to be equal to the final momentum, and initially we had a momentum of 0 kilogram meters per second. So that's your PI. Now let's talk about the PF. We said it's these two momentums. So you have an MV, mass times velocity for the gun, and another mass times the velocity for the bullet. And you know everything about the bullet. You know the mass and the final velocity, but you don't know the final velocity of the gun. So let's do that. All right, we plugged in our numbers, and now we have 5V1F is plus 11.25. That's going to be the momentum of the bullet. So the bullet has 11.25 kilogram meters per second of momentum. You would expect the gun to also have that much momentum, but in the opposite direction. So that's where we're going to subtract minus 11.25, minus 11.25. That's where this negative number comes into play. So now you have negative 11.25 is equal to 5V1F, and now we can find the final velocity. The final velocity of the gun is in the opposite direction, so that the momentums cancel out, but the magnitude is a lot smaller. It's only 2.25 meters per second. So that's not very fast, luckily. I mean, you do feel that the gun gets pushed back into your hand a little bit, but luckily it's not going as fast as the bullet. That would be crazy. You'd blow your hand off. But the important thing to know is that the momentums are equal. So this was V2F. That momentum is equal and opposite to this momentum, and we know that in this case because the initial momentum for the system was 0 kilogram meters per second. So when you add these two vectors together, they have to exactly cancel each other out so that you also have a final momentum of 0. That's the idea with these recoil type problems. So let's do number 2. Number 2 says a 2.4 kilogram block, so M1 is 2.4 kilograms, and a 7.2 kilogram block, so M2 is 7.2 kilograms, are initially at rest, so VI is equal to 0. It's like the gun and the bullet were at rest before, so the total momentum for the system is still 0. And they're on a horizontal frictionless surface. When a compressed spring between the blocks is released, the 7.2 kilogram block moves to the right at 0.5 meters per second as shown. Now it's important to note we called M2 7.2, and they're telling you the 7.2 kilogram velocity is 0.5. So after the collision, the second block is going 0.5 meters per second. So if you got this one wrong, maybe that's why, because they're actually asking for V1F the way I wrote it. So you just have to make sure you're matching up the correct velocity to the correct mass. So you write your equation, which is, again, just the initial momentum is equal to the final momentum. And the initial momentum of the system, they start together. So you have M1 plus M2. They're together, moving at the same initial velocity. And the final momentum is a combination of the mass times the velocity for the first block plus the mass times the velocity of the second block. If you add those two together, that'll give you the total final momentum, which should be equal to your initial momentum. In this case, the initial velocity is 0, so the whole thing cancels out. This whole term goes away. You're left with 0 is equal to, and this is for the first block, this is for the second block, so you have to be careful with your subscripts. So 2.4 times V1F is what they didn't tell us. That's what we're looking for. This is 7.2 times 0.5. So you could find the momentum of the second block. The momentum of that block is going to be 3.6 kilogram meters per second to the right. So the momentum of the other block is going to be 3.6 kilogram meters per second to the left. Is going to be negative, but how fast is that going to be? So again, you subtract by 3.6 on both sides. I'll write it over here. Negative 3.6 is equal to 2.4 V1F. Now you're dividing by 2.4, so you get a final velocity V. Let me write it over here, so it's like on part of the picture. V1F is equal to negative 1.5 meters per second. Okay. Number 3. In the diagram below, a 100 kilogram clown, so M1 is 100 kilograms. It's fired from a 500 kilogram cannon, so M2 is 500 kilograms. You could have flipped it. I called this one M2. This is 2. This is 1 in this case, the way I just wrote it. If the clown speed is 15 meters per second after firing, so V1F is 15 meters per second, what is the recoil speed of the cannon? So V2F equals question mark. They're looking for the velocity of the cannon. And it doesn't say that it's initially at rest, I don't think, but we can assume that the initial velocity is going to be 0 meters per second. So they didn't explicitly say that, so if you're having trouble with that one, maybe that's why. So we know that the initial momentum, well, I could write the whole formula again. Again, these problems are kind of like the inverse, the opposite of the inelastic collisions, because the objects start together, the clown is inside the cannon, and then they separate out into two separate things that have two separate momentums. So with this, most of the time, it's not going to be moving initially, so your total momentum for the system is going to be 0 pretty much every time. And this is going to be, I mean, unless the cannon is rolling initially, then you have some initial momentum to work with. But it's still the same process. So this is 100 kilograms times 15 meters per second plus 500 times V2F. So this is 1500, and then you subtract that. So negative 1500 is equal to 500 V2F. So the final velocity of the cannon is going to be negative 3 meters per second. And my computer's being a little bit slow right now, so it's like kind of being a little wonky with these things. It's like lagging behind. Sorry about that. But I have to try to rush and make this video quick because I got to cook dinner soon. But I got big tests tomorrow, so I got to make this video. All right, it says a 90 kilogram skater and a 75 kilogram skater stand at rest. So they're at rest. So the mass is 90 kilograms. The M2 is 75 kilograms. VI is equal to 0 meters per second. At the center of a skating rink, the two skaters push each other apart. The 75 kilogram skater moves with a velocity of 5 meters per second east. So that's the 75 kilogram one, which we called M2. Again, you have to be careful with how you're labeling your variables. So V2F is what they just told us. That's positive 5 meters per second because they're going east. And it says, what is the velocity of the 90 kilogram skater? So we'll call that V1F. And you got to be very careful with your subscripts here. So you got your equation, and you could substitute in the values, and now you could solve. So this whole side again turns into 0. So your total momentum for the system is 0 kilogram meters per second, and you have 90 V1F plus 75 times 5, which is 375. Now you subtract 375 from both sides, and then you're going to divide by 90 to get a final velocity of negative 4.17 meters per second. By the way, my fiance is the best. She just came home and she gave me not just a onesie, but a onesie that looks like an astronaut. So now I'm doing the rest of the video in my astronaut onesie. And if I reach, what should I say? What should we do? What's the goal? 200 subscribers? Let me get 200 subscribers and I'll do a 200 subscriber special in the onesie, and you guys will see what this awesome astronaut onesie looks like. I need 200 subscribers by the end of the school year. If I get 200 by the end of the school year, I'll be pretty happy. Should I make it 1,000 by the end of the school year? Oh, man. I don't know. We'll see. Let's see if I get 200 by the end of the quarter. That would be good. And then I'll show you guys this really cool onesie that I just got, and I'm wearing it right now, but you can't even tell. All right, number 5. It says, in the diagram below, carts A and B are being pushed apart by a spring. It exerts an average force of 50 newtons for a period of 0.2 seconds. It says, compared to the velocity of cart B at the end of the 0.2 second interaction, the velocity of the cart A is what? So a force is being exerted, an equal and opposite force is being exerted on both carts simultaneously. All right, so you have the same force. Try to draw out the same size vectors for the same amount of time. So what's happening is an impulse is being imparted on these guys, and they're gaining some momentum. So this gains momentum, and this gains momentum. But you have to be careful, because what is the initial momentum here? It says that they're at rest. So you have to say the initial momentum is equal to 0 kilogram meters per second. So that means that P1F plus P2F are also going to be equal to 0 kilogram meters per second. If you wanted to, you could rewrite this as Pi is equal to Pf, and we know the initial momentum for the system is 0 kilogram meters per second because they start at rest, and afterwards they separate. So you have P1F plus P2F. And so that's exactly what we wrote up here, but now we're using the form of the equation that we're used to. So let me get rid of this here. And now let's plug in, let's start rearranging this. So P1F is moving to the left, so let's subtract it from both sides. So you have negative P1F is equal to P2F. And what do we know? We know P is equal to MV, right? So let me move this up. So now we have negative MV for the first one is equal to negative MV for the second one, right? So we're just oh no, it's just positive because it's moving to the right, and that's what it is up here. All right, so we're just using the math to describe it. I'll describe it conceptually as well after this. So you want to solve for A or B. Let's see. The velocity of cart A is what? So let's solve for this variable. So V1F is equal to M2 times V2F divided by a negative M1. And now we have the velocity. Now we have the velocity of A in terms of all these guys. And let's plug in what we know now. So V1F is equal to negative M2 is 2 kilograms over 1 kilogram times V2F. So mathematically, we could see that the velocity of A is in the opposite direction because it's negative, and it's 2 times as great as V2F. So this one is moving slower than this one. A is 2 times greater than B. So if B is moving at 5 meters per second, to find A, you have to do 5 times 2. So you get 10 meters per second in the other direction. So let's see. It says twice as great. So we're going to do C. Now, like, here's another way to think about it, right? Let's go with just this. If we could get this far in our reasoning, and we got that way because, well, the initial momentum for the system is 0. So that means that when you add the momentum of this plus the momentum of that, they're going to cancel out and become 0. So basically, the magnitude of the momentum is the same, but this one is twice as big as this. So in order to have the same momentum, A has to be moving twice as fast to make up for it being half as great in terms of the mass. So conceptually, that's one way to explain it, but this is the math way to explain it too. So whichever way works best for you, or both. Number 6, a spring is compressed between 2 stationary blocks as shown in the diagram below. Block A has a mass of 10 kilograms. So let's use, I should have used A and B instead of 1 and 2 in the last one. Hopefully that wasn't too confusing. I'll try to use that here. After the spring is released, block A moves west at 12 meters per second. So VAF equals negative 12 meters per second because it's going to the left. And block B moves east, so VBF is 16 meters per second. What is the mass of block B? So MB is equal to question mark. And they're stationary, so technically we know that VI is equal to 0 meters per second. So that was in there too. All right, so same business as usual. The initial momentum is equal to the final momentum, so we write it like this. So this is 10 plus, we don't know the mass of B. So this was kind of tricky, but this at least cancels out to 0, so this whole side becomes 0. And the mass of A, again, is 10 times negative 12 plus the mass of B times 16. So you have negative 120. Well, all right, so I almost fell into the same trap that some of my students do, right? So this is 0 on this side is equal to negative 120. Sometimes they'll just write the negative 120 on the left side of the equation, but you'll see that why that's wrong right now. So this is 16 MB. What you want to do is add 120 to both sides, right? So this becomes positive 120 over here is equal to 16 MB, and you get a positive number for the mass, which is a good thing because mass should be positive. So the mass of B is 7.5 kilograms. All right, number 7 says the diagram below. So M1 is 10 kilograms, and M2 is 15 kilograms, and V1I is 3 meters per second. So, oh, this isn't really a recoil type problem. What's happening? They're coming towards each other. They start separate. They come towards each other. So V2I is 3 meters per second, but to the left. So we make that a negative number. That's important. All right, it's going to the left. So that's negative. And it says, when the 2 carts collide, they lock together. What is the magnitude of the total momentum of the 2-cart system after the collision? Now, they're not asking. They say they lock together. So is that elastic or inelastic? You should know it's going to be inelastic because they stick together. If it was elastic, they would bounce and separate. All right. And normally for 9.4, that homework assignment, they would ask, okay, how fast do they move after the collision? How fast are they moving? But watch, it says, what is the total momentum? They don't care about how fast you're moving. They're asking for the total momentum of the 2 blocks when they are moving together. So you're looking for PF. All right, and if you look at what the whole idea is, that we're saying that the initial momentum is equal to the final momentum. And there's your PF. So that's really what you're solving for. So if you just wrote the equation down, maybe you even realized it was this equation. And maybe you even solved for the final velocity. But then you'd have to multiply it by the masses, the combined masses, in order to find what they look for. Maybe you didn't even realize, maybe you did all that work and forgot what they were actually asking for was the total momentum PF. So instead of like just having like muscle memory and writing the equation, it's important to realize what we're talking about here. They're looking for the final momentum. So why even plug in all this stuff over here? Let's just keep this side of the equation the final momentum. This is PF. I got a car alarm outside. Hopefully you guys can't hear that. It'll be annoying. Hold on. Okay, I threw something at the car and it stopped. All right, so now we have an equation that we could work with, and mathematically it'll work out. And I know you guys like it when I explain both ways, right? So now I'll take some time and explain it conceptually. If they're looking for the total momentum after the collision, we should know that's equal to the total momentum initially. So basically what you're doing is you're calculating what the initial momentum of the system is. So you could calculate the momentum of this guy plus the momentum of this guy, and that's the total momentum for the system, which is the same before and after the collision. So that's a different way. Don't get too bogged down in the equation. You should know like what we're talking about here. Okay, so you substitute in. And don't forget to make this a -3 because they're going against each other, right? This one's going to the left, so we make that negative. Then you get 30 is equal 30 plus -45. So minus 45 is equal to PF. So the final momentum and the initial momentum is equal to -15 kilogram meters per second. The total momentum when you add both of these guys together, right? Because this guy has a momentum of 30 kilogram meters per second, and this guy has a momentum of 45 kilogram meters per second in the opposite direction. So the total momentum is equal to -15. The momentum vector, the total momentum, P total, for the whole system is to the left, 15 kilogram meters per second to the left. All right, so this was a tricky one. Everybody's coming to the, okay, number 8. Here we go. In the diagram below, a block of mass capital M is initially at rest on a frictionless horizontal surface, and it's struck by a bullet of mass lowercase m with a horizontal velocity of v. What is the velocity of the bullet block system after the bullet embeds itself in the block? So after, this is the initial condition, and then the bullet embeds itself in the block and they move together. All right, so the bullet sticks into the block, and now they're moving, but maybe not as fast. Definitely not as fast. You have some different final velocity going this way. I'll even draw the velocity vector is smaller because it's not going as fast as the bullet was before, because now their masses are combined. So yeah, and it says give your answer in terms of these guys. So it's tricky because you don't have any numbers to work with, but you want to just solve for VF the same you would normally if you do have numbers. So I'll show you what I mean. So just like before, we have M1 and we have an M2, but now they're telling us, well, this is, we'll call that M1. So this is the lowercase. And then this is M2. All right, I just did that because this is the first one and this is the second one based on the picture. So you could switch it. You could call either one. All right, maybe M1 is capital M. Doesn't matter. So now the initial velocity of the bullet is going to be V, right? So we call that lowercase v. And yeah, then we don't know what VF is. So we have to solve, right? Now, initially, we have the initial momentum for the system is equal to the final momentum for the system. Initially, we have two separate things. So we need to do two separate momentums. We have P1I plus P2I is equal to P1 plus 2 together, F. You could write it that way if you'd like. So P1I plus P2I is equal to that momentum there. So here we go. We have mass times velocity plus mass times velocity. And then we have the combined masses times VF. And this was for 2 and 1. 2, 2, 1, 1. This is the initial. So again, this is the initial momentum for block 1. Sorry, for the bullet. Initial momentum for the block. And now we're off to the races. It's the same thing, but you're just plugging in letters instead of numbers. So we called M1, that's the lowercase m. We called V1I is just a lowercase v, plus M2 we called a capital M, and we didn't write it down, but we could. V2I is 0 meters per second. So this is times 0. And this is equal to, again, lowercase m plus capital M times Vf. Now, we do have a number in there, it's 0, so we can try to use that. That cancels out. We're left with mv is equal to m plus capital M times Vf. And we want to know what Vf is, so we solve for Vf by dividing both sides by m plus m. M plus m. Those cancel out, and you're left with Vf is equal to m times v over m plus capital M. And that's your answer. So you could totally write it like that. Sometimes you'll see it written where they'll take out the v and they'll put it over here. And they'll do one of these guys. And this is totally valid because you got to remember how you add fractions. If you write the v out here, you're multiplying by a v. Well, this is really like v over 1. And the way you multiply fractions is you multiply everything in the numerators and you multiply everything in the denominators. And since the v is over a 1, you still get the same thing in the denominator. But now you have m times a v in the numerator. So you could totally write it like this. That's valid like that. And if you really wanted to, you could even write it like this. But they don't really do that as often. Why is this a more useful term? Well, now you have all the masses in the parentheses here. So it's kind of like a nice thing to put all the masses together in one thing. All right, that's about it. Have a good day.